Alright, so in this short video, we're going to be looking at the reactions of alkenes with simple alkenes such as propene. Right, we're going to be looking at propene. Yeah, simply because it's an asymmetric alkene. So we're going to be looking at the difference between the reaction of propene with hydrogen halide, right? Looking at Markovnikov and anti-Markovnikov products, and then just looking at the reaction of propene with probably just a molecular halogen. Alright, so propene's general structure looks something like this: 3 carbons, 1, 2, 3. Right, propene. Right, so it has this one double bond there, and it's connected to some hydrogens. Let's put in all the hydrogens now. That is the structure of propene. For ease of drawing, right, and ease of explanation, I'm going to be drawing propene like this. Right, so a simple structure like that. Okay, so this is a skeletal structure, right? A lot of persons don't really adhere to the skeletal structure like that, I notice in CAPE, but it basically means that this is a shortened version of what's happening up here. So this would represent, let me see, on a larger scale, a carbon bonded to 2 other carbons, right, and hydrogens, right? So I'm just going to be using that skeletal structure to give the explanations here. So let's look at propene. So propene is what we know as an asymmetric alkene, right? So if alkenes are asymmetric, or show asymmetry, how halides, hydrogen halides, like hydrogen bromide for this example, reacts with this substance is going to react in 2 separate ways, because there are 2 separate products that can arise. Now, one product is much more likely the major product, or what we call the Markovnikov product, and then the product that is less likely to be formed, the minor product or the anti-Markovnikov product, can be found. Alright, so let's look at how this genuinely reacts. Right, now we know that, let's start with our reagent, right? Hydrogen bromide. Actually, we know that bromine is a halogen, right? And hydrogen, right, is on the other side of the periodic table. Hydrogen's electronegativity is really small compared to bromine's electronegativity. And what we normally know about electronegative atoms is that they have the higher tendency to attract electrons. So what will happen here is that the electrons within the bond between hydrogen and bromine, right, will actually move closer to the bromine as it's more electronegative. Bromine will now bear a slightly negative charge, hydrogen a slightly positive charge. Right, now this will affect the high electron dense region, which we call the double bond, right, on this alkene here. So what will happen here is that there will be something called an electrophilic addition, and that's actually the mechanism of this type of reaction, an electrophilic addition. So if the electrophile, the positive species, right, interacts with the negative area, right, we're gonna have electrophilic attack. So hydrogen in this case would be the electrophile because it has that slightly positive charge. So what will happen here is that the electrons in the double bond, right, will be attracted to hydrogen. Right, so that's one pair of electrons going over, right? And so what will happen here is that as the hydrogen comes into the molecule, the propene per se, then this hydrogen bromide bond will actually break, and it will actually break heterolytically, right? Heterolytic fission speaks to the fact that both of the pairs, or the electron pair in the bond, right, moves towards one species. So one species gains both the electrons that are participating in the bond, right? That is heterolytic fission, and it usually happens within polar compounds when they're cleaving, right? So since bromine is more electronegative, we know that both of these electrons will be moving on to the bromine, right? So what we're going to have happening now is something like this. So it can either go one of two ways. One of two ways. The hydrogen can bond to the molecule and allow this carbon to be slightly positive, or it can bond to the molecule and make this carbon slightly positive, right? So what's happening, our new hydrogen that is being added can either be added there or added there. Now, there is a difference between these two products, right? Or these two intermediates, rather. Now, one intermediate is much more stable than the other, right? As we spoke about before in the reactions of alkenes class recording, we will be looking at the fact that a tertiary carbocation, right? So a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, right? And this is based on how many carbons, right, our carbon with the positive charge is attached to, right? So it depends on that. So in this case here, this molecule, this is a primary carbocation because this carbon bearing the charge is only attached to one other carbon, right? In this case, we have a secondary carbocation because the carbon here bearing the positive charge is attached to two separate carbons. Therefore, the secondary carbocation here will be able to distribute the charge a little bit better. The more alkyl groups that you have to donate electrons to the positive charge to diminish the high positive charge on that carbon rather, right, the more stable the species. So we're going to be looking at this. Let's look at the first one, all right? This first one, right, the secondary carbocation is produced through Markovnikov's rule. So let's have a look at Markovnikov's rule. So Markovnikov's rule states that the hydrogen atom, or the proton, sorry, right, will be added to the carbon with the most amount of hydrogen, right? So it will be added to the carbon with the most amount of hydrogen. So if we were to draw this structural formula, right, draw it out a little bit more, what we're going to be having is a species like this. So let me center it a little bit better. We're going to be having a species like this. So the double bond was once here. That double bond is now broken. Let me just draw in the hydrogens before I start explaining. Right, this double bond is now broken, right? So Markovnikov rule states that this hydrogen here will be added to the carbon with the most amount of hydrogen. Now, this carbon has two hydrogen and this carbon has one hydrogen, right? So it will be bonded here. So this is our new hydrogen atom, right? And now, well, hydrogen group. Now this carbon here will bear the positive charge. This is a secondary carbocation, right? And this is much more stable, right? The more stable something is, the more likely it is to occur. So Markovnikov's rule really states out, well, helps you find the most, the most plausible product or the most stable product, right? The major product. That's what the Markovnikov product is, right? Now, what will happen now? Let me just erase this to show what will now happen to this. Since we know that there's going to be a positive charge here, right? The bromide ion is going to remain here negative. This is a nucleophile because it's going to be attracted to that positive charge there. So the electrons on the bromide ion will now be attracted to that positive charge there on the molecule, giving rise to this molecule here. Alright, that is the end product. This is a major product. Alright, in case it's not being seen properly, let me just draw it up a little bit more. Alright, this is the major product. Alright, so this is a simple 2-bromopentane. Right, so 2-bromopentane is our major product in this case. This is our Markovnikov's product. Now, what our anti-Markovnikov's product would be is basically ignoring the Markovnikov's rule. So in this case now, let me just draw this briefly. In this case now, we'll be adding the hydrogen to the carbon with the least amount of hydrogen atoms, right? Leaving the positive charge on here, creating a primary carbocation. Right, now this primary carbocation is going to be less stable and less likely. Therefore, this is our minor product. It occurs less, right? So our anti-Markovnikov intermediate, right, will give rise to our anti-Markovnikov's product, which is our minor product. So what we're going to end up with, right, is this product. Well, it's not going to be looking like that, which is 1-bromopentane, right? So that is our anti-Markovnikov's product. Anti-Markovnikov's product. Alright, so that's basically it. Now, the general thing, right, about understanding Markovnikov's addition, right, is that what the Markovnikov's rule is stating that hydrogen, right, that in this case is the electrophile, hydrogen adds to the carbon with most amount of hydrogen attached. Really, right? So if we follow this rule, we end up with a more stable species. If we don't follow this rule, right? So if we don't follow this rule, we're gonna end up with a less stable species. This is an intermediate, by the way, the carbocation intermediates, right? And this really states out whether or not something's gonna be the major product or the minor product. Right? So this is major, this is minor. And that's really it. Just remember the Markovnikov's rule of, my bad. Just remember the Markovnikov's rule, right? How that works, the difference in stability of the intermediates, right? And the fact that this is an electrophilic addition mechanism, right? Because the electrophile, which is our hydrogen, is going to be adding to the molecule first. So when the electrophile adds first, right, we call it an electrophilic addition. So that's it.